All right, welcome back to another video. This is the third part of electromagnetism 1. And in the last one, we were looking at the left-hand rule and the movement of charged particles. And now we're looking at the real crux of this chapter, which is the loudspeaker and the DC motor. So let's get right into it. Now, sometimes this is asked in questions that where do we see the applications of this idea, which is called the force on current carrying conductors. So it's basically in two places in your syllabus. One of them is the loudspeaker, the other one is the DC motor. Let's have a look at it. So this is what the structure of the loudspeaker looks like. You have a clamped magnet. So this E-shaped structure is a magnet and it's clamped on both sides. So it's held in place. On this middle part of this E, there's this cone and it's basically wound around this using a coil of wire. And what's going to happen in this coil of wire is that some current flows here, right? And it could flow in any direction for that matter. But what you do need to remember is that as we plug in any AC appliance to some any appliance to some AC supply, so we know that alternating current flows through that, right? So the current which is flowing through this coil is alternating. Now, how do you explain how this loudspeaker works? So we know that if the current is alternating, then the field that it gives rise to is also going to be alternating. What do I mean by this? Is let's say if current is sometimes flowing like this. So for example, using right hand grip rule, I can see that this is where my thumb points. So sometimes this is the North Pole. And other times when the current flows in the other way, then this is the North Pole. So the current and hence the field keep changing directions. So it's constantly changing. Now this produces an alternating field. And you also have the field of the magnet in itself. So when the alternating field interacts with the field due to the magnet, which is fixed, this also produces an alternating force. So what this alternating force means is that sometimes the force on this coil is sometimes it's forwards, other times it's backwards. So this cone and hence the coil with which it is attached, it's sometimes moving forwards, it's sometimes moving backwards. So this causes the coil and the cone to which it is connected to move back and forth. Now this is now linked to the chapter of sound, the videos for which are already on the channel. So we know that when the cone pushes forwards, so the air particles come closer, this creates compressions. And similarly, at other times when the cone pushes back, this creates rarefactions because the air particles get further apart. This is also written here and it's exactly taken from those notes. So as the cone moves forwards, air particles are pushed together, creating a compression. And we know that here the air pressure is greater. And as the cone moves back, air particles move further apart, creating a rarefaction where we know that the air particles are furthest apart, leading to the lowest air pressure. So that's the idea of the loudspeaker. What about the DC motor? So this is like a really beautiful diagram of the DC motor and all its components. So first of all, what is the DC motor basically comprised of? So you have your fixed magnets here, right? So your permanent magnets, they are made curved in some older drawings of the DC motor in your book. And that is basically to ensure that it produces a stronger field. Because if you have curved magnets as compared to straight ones, so with straight ones outside the magnetic field lines could curve, but if you keep them curved like this, so there's a lesser area between them, so the magnetic field strength is stronger and is constant. So that's the reason for this. Another important component is the coil of wire in between here. So this is a coil of wire which I've already labeled as A, B, C, and D. And right now let's not talk about these. And let's say this is connected to some battery, to some cell. So what's going to happen in this case? So first of all, you can see that with the battery, this is the positive end, this is the negative end, and I can already see how the current is going to flow here. So it's out of the positive end into the negative end. So it's going to flow like this, back again, like this, down here, and back to the negative terminal. So this basically then fulfills the requirement of what is called the motor effect, which is that if you have a current carrying conductor in some magnetic field, it's going to experience a force. So current carrying coil between the magnets will experience a force because of the interaction of magnetic fields. By Fleming's left-hand rule, we can now determine how this coil will rotate. Again, let's start with side AB. So I know that my field points like this, which is also shown in gray, and my current in the side AB is actually out of the page, right? So it's pointing out towards me. So then what I see is my thumb points up. So the force on this side is upwards like this. And then obviously on force on side CD, again, this is how the field is still, but the current actually is into the page this time. So this side CD experiences a downward force. So there's an upward force on AB, there's a downward force on CD. So that causes it to rotate because both of these combine to produce a moment on the coil. So by Fleming's left-hand rule, force applied on side AB is upwards, and on side CD is downwards. And you can see the kind of moment this produces on the coil because it's going to rotate like this, right? So this is how it's going to rotate. So we'll say this is a clockwise movement. So this causes a clockwise movement on the coil. Why am I not talking about sides B, C, and AD? Because the requirement is that for Fleming's left-hand rule to hold, the current and the field must be perpendicular to one another. So then we get the force which is perpendicular to both of them. But with sides B, C, and CD, the idea is that these are carrying current parallel to the magnetic field. So parallel means that the field is also like this and the current is also like this. So if they're in the same direction, they don't really experience a force. So this is what I would say here, since they carry current parallel to the field. The other ones carry current perpendicular to the field, so they do experience a force. Okay, next. The maximum moment on the coil. Okay, so how do we talk about the moment here? Is let's say that this is some distance d from the coil, this is some distance d from the coil. Let's right now restrict ourselves to the horizontal orientation of the coil, and then we'll talk about what's happening when it's not horizontal. So I can see that this axis is basically like my pivot here. In my moments chapter, this is what I talked about. So if this is my pivot, I know this is the distance, the perpendicular distance from the pivot, and the force, and this is the force. So that's the formula of moment. Force multiplied by perpendicular distance from the pivot. So that's Fd. And if I look at the moment it's creating, obviously that's clockwise. If I look at this one, so again, this is the force F, perpendicular distance is d, so that's also Fd. So that's both of these combining to produce a clockwise moment, so that's going to be Fd plus Fd, which I can write as 2Fd, but for a moment I'm going to write this as F times 2D. Why am I calling it this? Is because isn't 2D really just the width of the coil? Yeah. So I can write it as the force on one side multiplied by the width of the coil. This is the maximum moment. It's not always equal to the same moment. And the idea is that the moment on the coil gradually decreases as the distance from the pivot decreases. Now let me show you this using something like this. So let's say that this pencil here, it's the pivot, right? Now as this starts to rotate, you can see that initially it's all of this distance, right? It's all this distance which the force has from the pivot. But as it keeps rotating, this perpendicular distance starts decreasing because this is where the force is acting, right? On the edges. So as it rotates, it's now not going to have as much of a moment because the distance is decreasing. So initially it's all of this distance, But let's talk about something like this. So now the perpendicular distance is only this much. So because the distance decreases, the moment also decreases. And then gradually, if you think about it, when this coil becomes vertical, so if this is again its pivot, its axis, and if it's like this, right? So in this point, this is how the force would be acting. But if this force, if I think about it, this force is now actually passing through the pivot, right? So it's not going to have any moment. So when this becomes vertical in a position like this, for example, right? So if this is how the force would be acting, it would actually be passing through the pivot, so it would not produce a moment. So that's the idea here. So in the vertical position, there is no moment on the coil because distance from the pivot is 0. However, even though the moment is 0, previously it would have gained some speed, or in terms of another quantity, it would have gained some momentum, which is going to take it past the vertical position. Now, let's say if we did not have these here, and this is going to bring us to this idea now. If it was rotating in the same direction, and let's say it comes here. So this is A and this is B. And if these are connected using wires, then the direction of the current in AB would still be downwards. Okay, sorry, this is A, this is B. So the direction of the current would still be downwards like this, right? But now if the direction of the current is downwards, what does this mean? So this means that this would now experience an upward force. So would the motor just keep rotating like this? Would it never go through an entire turn? That's the reason we have a split ring commutator in place. Because what the split ring commutator does is, as you can see, this is also attached to the coil and these rings are also turning. So when this actually rotates, there would be a time when this is in contact with this part and this is in contact with this part. So what it does is, now when AB is here like this, previously the current through this would be like this, but now when it's on the other side, it reverses the direction of current in each side of the coil. So now through AB, the direction of the current would be exactly like this to keep it turning in the same direction. Because if I take this direction of the current and if I figure out the force, it's going to be downwards, which is exactly what I want, to always keep it turning in that same direction. That is the function of the split ring commutator. A lot of the people, they also get confused with the split ring and the slip ring. So keep in mind that when you have one ring which is cut into two, that's called a split ring, right? And in the case of the AC generator, you have two different rings. Those are called slip rings. So this is singular, that's plural. And the carbon brush, it's just basically a method by which electrical contact is maintained with the coil and the battery to keep current continuously to ensure that current is continuously supplied to the coil. So that's the idea here. So the speed, the momentum of the coil takes it past the vertical position. That's also shown in this diagram here. The things that we talked about. So initially it was all this distance, right? So if the current was basically going in through this part, out through this part, this is exactly what's also shown in the diagram, because the current was flowing from A to, okay, just a minute. Again, I may have made a mistake. No, actually this is fine, because this is current out of the page, this is current into the page. Apologies, I do get confused with this. So this is out, this is in. So yeah, this is exactly how the current is flowing. So at first it's all of this distance from the pivot, right? So this is how it's rotating. But then as it gets more and more vertical, this distance reduces, because now it's only this distance, which is obviously less than this. And when it gets vertical, so the force which is now acting is passing through the pivot, so it doesn't produce any moment. What does the split ring do? So the split ring commutator reverses the direction of the coil every half rotation. So when it goes from this to this, it reverses the direction of the coil when it passes the vertical to keep it rotating in the same direction. The split ring does not rotate itself, and the carbon brushes provide contact between the source and the coil. And by the source, I mean the battery or the cell. The factors affecting rotation. So how can you increase the turning effect, the speed with which this coil rotates? So obviously the factors affecting force are still there. So for example, the magnetic field strength of the magnets through between which the coil is placed. So that's still there. The current in the coil, which you can increase by, for example, using a higher voltage supply. The third one, the length of the conductor. But again, with the length of the conductor, think about it this way. If I just increased this length, it really doesn't increase the force because I'm talking about the length of the conductor in the field. So if this part and this part are already protruding out, it doesn't make a difference. So how we tackle that issue is by having turns on this coil. So with turns, you again have a greater length of the conductor which is in the coil. So also if you increase the turns, so more turns on the coil, that also increases the force and hence the rotation. And the last one is if you have a soft iron core placed in the coil, this also serves the same purpose, because when the soft iron core, when the current is going to flow, the soft iron core is also going to be magnetized. And you know this idea that induced magnetism is always attractive. So that and this magnetic field strength are going to add up. There's going to be a greater magnetic field strength and hence a greater force. Right? So it says that all of these increase the strength of the field of the conductor, which increases the force experienced by the coil. Right? So a stronger magnetic field strength naturally also means a stronger force. But there's also another one, which is making the coil wider. Now, what does this do? We just saw that the moment is the force on one side multiplied by the width of the coil. So if the width of the coil goes up and if the force stays the same, then there would be a greater moment as well. Because just by that moment's formula, you now have a greater distance from the pivot, so the moment goes up. So making the coil wider, let's talk about this. So increases distance from pivot, increasing the moment. So this is the only factor which does not affect the force, but it still affects the rotation of the coil. So this is something important. So that's like a really quick summary of all the concepts and ideas related to electromagnetism 1, which was everything related to the motor. Now in the next couple of videos, we'll be talking about electromagnetism 2, which is ideas related to the generator effect. So the AC generator, transformer, EM induction, the laws of EM induction and whatnot, we'll be seeing there. So thanks for your time. Hope this cleared some concepts up, and I'll see you in the next video. Bye.